Hello everyone, very warm welcome. So today we are starting a new topic in our series and it will be on trees. I'm pretty much sure that most of you must have heard about this before. If not, that's absolutely fine. We are going to cover every small aspect so that you understand this concept thoroughly. So in today's video, we are going to cover three topics. First is introduction about the trees. What are these? What are its applications? Then different types of trees. We will also discuss where these different types of trees are used, and then application of trees in computer science, where this data structure is used and why it is so much beneficial. So without wasting any further time, let's start with today's lecture, and it will be on introduction. So as the name suggests, tree means you can visualize is like a physical tree that you can see on road on in or in your park, but just make it upside down. So generally trees have roots on the ground. To visualize a tree in computer science, you can assume that the root is there at the top, right? And from the root you can have many branches. Okay? And then we when a branch connects two nodes, basically we can say that. So there is another node here and then it can have further branches. Typically in computer science we always start with root, and from the root you decide where I want to go to find out the next node. Okay, so root we can say is the starting point of the tree. So if I want to write the definition, so I can say that tree is an abstract data structure that simulates a hierarchical tree structure. So the word hierarchical is very important here. It describes that you have to start from the root and there is a hierarchy of nodes that you must traverse to reach the node that you are looking for. So we have to make sure we keep these things in mind. This is the first one. This is the second one. And third, we can say that it is widely used where we need to reflect or maintain the hierarchical relationships. So this is about the introduction of the trees. Uh, some of you might say that this visual diagram that I have drawn, um, it has so many branches. Generally, trees have two. No, a tree can have any number of branches. If you are saying tree is having two branches, that means it's a binary tree. That is the most commonly used, but it is not the only one that is used. Okay, so that confusion should be removed. What you should focus on, that you always start from the root, that is your starting point, and then wherever you want to go from the root, first of all you start from the root here, then you traverse the path. Suppose there's another node here, some here. Wherever you want to go, you have to traverse this path. And this is the node suppose you are looking for. So this is your path from the root to, say this name is 1, it is 2 or 3, and this is 4. So from the root, you go to 1, 2, 3, and 4. And there will not be any other path present to reach to 4. This is very, very important. And that's what differentiate tree from a graph. There will be only one path, a unique path between any two nodes of the tree. With this, let's move to some other one. So I can say that we have covered the introduction. Now let's see what are different types of trees. Different types of trees. In this, I will also explain where these are used. So first one is a binary tree. This is the one that I would say most of you have seen. So a root here, something like this. This is a binary tree because each node is having two paths to go from. One is called generally left, another is called right. This is called a binary tree. There is one more category you can say is called complete binary tree. So the properties of complete binary tree says that all the nodes should be filled except at the last level. So here we have 4 levels. First level, second level, third level, fourth level. Right? So you can say that all the nodes are filled except the fourth one because here all are empty. Also, even if the nodes are there, then from the left hand side they must be filled. This is also a complete binary tree. But if I draw a node here, now it is not a complete binary tree because these are not completely filled from the left. Okay, this is the properties of complete binary tree. So I'll remove this so that we can keep our tree simple. In case of tree, or you can say binary tree, you can say the height of the tree will be log to the base 2 of n, where n is the number of nodes. That is the height of a complete binary tree with n nodes present. Next type of tree is called binary search tree. This search term is very important. And as this terms is signifying, it is used for searching. Now let's see what is a binary search tree. I'm drawing a tree and then I will explain you the properties from it. So the property of binary search tree says that for the tree and each subtree, when I say subtree, I am referring to this part. This is a subtree. This is also a subtree. This is also a subtree. And this is the entire tree. Okay, let me undo this. So for a binary search tree, it says that the left nodes should be smaller than the root and right nodes should be greater than the root. For all sub trees. So if you take the example that I have drawn, we have 20 at the root. Now all the nodes that are left of 20 in this entire subtree, they should be less than 20. And the nodes which are at the right, they should be greater than 20. When we come to the subtree, say this one, now consider this is your new root. Here also, all the left node should be less than the root, the new root which is 10 here, and at the right they must be greater. So this property should hold for each and every subtree. Then it calls a binary search tree. And it is widely used in searching. That is why it is called search, because this will give the search time in log n time complexity. Because suppose you have to search 40 here. So at each step, you can just neglect half of the elements. When you are at 20, you are searching 40. One thing is sure, that it won't lie in the left region at all. So you can entirely neglect it. And if the tree is very big, then at every step as you move down, you will be able to neglect half of the leftover nodes. So assume you want to search 25. You start from the root. 25 is greater. Neglect the left part and move towards the right. Now compare 25 with 30. 25 is smaller. So neglect the right part and move forward. So at one point, either you will say that if you reach the leaf, either the element is not present, or you can say that I'm able to find the element. Okay. So this is the difference between a binary tree and a binary search tree. Always pay attention to the word search, whether it has been provided or not. In binary tree, elements can be in any order. They can be present anywhere. There is no relationship between where the smaller one will go or where the greater one will go. Let me remove this. Fourth type of tree we can say are self-balancing trees. There are two types mostly used, AVL and RB. This stands for red black tree, and AVL tree is for the name of the person who first invented those. So when you call self-balancing trees, what does that mean? I will explain quickly. Suppose this is your tree. This is a complete binary tree. But assume that your tree is not a complete binary tree. Then what the problem here is, you are wasting a lot of space because you are not using all the pointers that are associated with each nodes, and height of tree also becomes more. And if tree is not balanced, then if you try to search in them, then it will be a linear time complexity because you have to traverse the entire path. If the tree is not balanced, then you have to traverse the more path. Or if not here, if you suppose you want to traverse from here, here. So you have to take 5 steps. But if this is a balanced binary tree, then maybe you would be able to search this in only 3 steps. If these 4 nodes are present here, right, and you do not need all these 4 nodes, now this is a balanced binary tree, a complete binary tree. Now, if you want to search something, you would be able to search in only 3 steps. And when it was not balanced, it was taking 5 steps. So when you make your tree balanced and you want to search something, then your time complexity improves. And one more point is that RBT is generally used in C++ STL implementation of map or set. This is implemented as RBTs, red black trees. Okay, let me remove this. Fourth is done. So fifth type of tree we can say are heap. So I have covered heap in too much details. I think there are 3 or 4 videos on it. So I would request you to please go through that. A heap is something which is implemented as an array. But visualized as tree. So I have devoted 3 big videos on it. I will put the link in the description below, and maybe you can go through those if not already done. Next type of tree is called Trie, Trie, Trie. This is basically used for dictionary. wherever you have to implement dictionaries, or where you think that there can be sub words that can be formed, there you use trie. So for example, if you want to store something, say sharp, now SHARP, now assume the word is sharpen, so it would be, if the word is, let me write sharp separately, if the word is shape, then it will be formed like this. Like, so if you want the word, so if you see the dictionary, that's how the dictionary is formed. You can have as many branches from a node, at max 26, so that you can form different words. So if you say, let me take example of another word, shoot, so you will branch from here. So can you see that how we can extend this trie very efficiently? If I go with the implementation, it is going to take at least 1 or 2 videos. So we are just understanding the concept here. Let me remove this. Next type of tree we can say is an array tree. An array tree means where a node can have any number of child. So binary has only 2, an array tree can have as many as long. So there is something also called a B tree. It is widely used in databases, and it can have more than 2 child, 3 or 4, depends on. Those are so B trees are something which are specifically designed for databases. They do the very effective searching. There can be many more, but we have covered only 7. These are, maybe you can say, the common ones for the different type of trees. With this, I think we have covered second part also. And let's move to the third part, which says what are the application of trees in computer science. Application of tree data structure in computer science. So first of all, I think you are familiar and you must know it is widely used in searching. Why? BST property that we just above saw. Yep. You are already aware of this. Second is sorting. Can you guess where it is used? Heap. We already covered that. Heap sort is based on that. TrieTQ, I can just write it as a extension of heap, so I'm writing just here only. In your routing and decision making, we use trees. So decision trees or trie come into this. There is one more thing called segment trees. Segment trees are used where you want to find the sum of a range or something about a range, where you want to find some details about a range in very quick time. Their segment trees are used. Huh? So I can explain all these things in a separate videos, but here we are just listing down where all these are widely used. Fourth, we can say wherever we are organizing or playing with structured data, there we widely use trees. If you take the example, I can say XML. XML is entirely based on tree structure. It has a hierarchy relationship. Or you can say the HTML DOM, document object model. It is entirely based on trees. You have a panel, and then you go into that, you have sub panels, and that's how you design those. And one more is, you can say, organize your data, structured data is your files or directories on your disk. So these are very common, widely used applications of trees in data structures. They can be huge. I mean, each one can have more and more subcategories, and we can cover those in different videos. If you have any a specific topic, then let me know. I will cover those. So with this, I would say for today's lecture, we have covered our 3 topics. I will see you again in the next lecture. Till then, please take care of yourself. If you have any questions, do let me know in the comments below, and I will see you again in the next lecture. Thank you. Bye.